We have already discussed Lagrangian formulation of mechanics, and you have derived the Lagrange equation of motion for a conservative system and for also a non-conservative system. Today our concern is regarding the Lagrange equation for a conservative system. You have studied in previous lectures that Lagrange equation for a conservative system is written in this manner. This is d dt del L by del qk dot minus del L by del qk equal to 0. I have mentioned it here. This is actually known as Lagrange equation for a conservative system. In this equation, actually L is a Lagrangian of the system, which is defined as T minus B, where T is kinetic energy and V is potential energy of our system. And the QK is actually generalized coordinates, and QK dot, which means dQK by dt, that is generalized velocities. This K runs from 1 to F, where F is the number of degree of freedom of the system. So you have a knowledge of this Lagrange equation because you have already studied it in previous lectures, and particularly this Lagrange equation is for a conservative system. Now we have studied the Hamilton's variational principle, and Hamilton's variational principle is applicable for holonomic conservative system. So it is possible to deduce this Lagrange equation for a conservative system from Hamilton's variational principle, because this principle is applicable for conservative system, and we want to derive the Lagrange equation for a conservative system. So it is possible that we can easily derive a Lagrange equation for a conservative system from Hamilton's variational principle. So in this regard, I will discuss actually two methods. The first one is very brief method or very short method. You can see here. As you know, according to Hamilton's variational principle, the time integral of Lagrangian of the system is extremum. Mathematically, you write it I equal to integral from t1 to t2 L of qk dot t dt equal to extremum. As I have told you, these qk's are actually generalized coordinates. If f will be the degree of freedom, then actually this qk will have f values from q1 to qf, and similarly this qk dot will also have f values from q1 dot to qf dot. Now if we will take the delta variation of this integral I, then according to Hamilton's principle, delta I equal to delta integral from t1 to t2 L of qk dot t dt equal to 0. We have already studied it in the heading Hamilton's variational principle. Now from calculus of variation, we know that when I is extremum, then Euler's Lagrange equation must be satisfied. You have discussed this fact in very detail in earlier lectures. And what is that Euler-Lagrange equation? This is d dx del f by del yk dot minus del f by del yk equal to 0. Actually here this Euler's equation is for the case of several independent variables. Here yk are independent variables, and if k is degree of freedom of the system, then k has f values, and so here f which I have written here f, that f is actually the functional, and this functional is actually a function of yk prime and x. You know it. Now if we compare the present problem here, then at the place of L, in fact there is f, or you can say at the place of f there is L, and at the place of yk there is qk, at the place of yk dot there is qk dot, and at the place of x there is t. So you can compare these two results, that x at the place of x, as I have told you, there is t, instead of f there is l, instead of yk there is qk, and instead of yk dot there is qk dot. So if you want to write the Euler's equation in this condition, what will be that? You can simply replace the variables from here and you can see the Euler's equation in this condition can be written as d dt del L by del qk dot minus del L by del qk equal to 0. And as I have mentioned earlier, you know, in fact this equation 3 is nothing, this is simply Lagrange equation for conservative system. Lagrange equation for conservative system. So you have seen how easily we can derive the Lagrange equation for conservative system by the use of Hamilton's variational principle and the technique of calculus of variation. So this is a very short method and you can easily find Lagrange equation by this method. Now we will see another method which is just a rigorous method to find the Lagrange equation for a conservative system. You know, the Lagrangian of the system in general is a function of qk, qk dot and t. So you can write Lagrangian of a system is given as L equal to L of qk, qk dot and t. Now if this L is not an explicit function of t, or in other words, if you can say that if L does not depend on this t explicitly, then actually L will be a function of only qk and qk dot. So if L does not depend on t explicitly, then we can write L equal to L of qk, qk dot, and therefore what will be this delta L? As you can see, L is not a function of only one variable, but it is a function of more than one variable here. Actually, this is a function of two f variables. The number of qk will be f and number of qk dot will be also f. So actually this L is a function of two f independent variables. So in this condition we must follow the rules of partial differentiation to find this a small variation in L, which is delta L. And so you can write, following the rules of partial differentiation, this will be summation k equal to 1 to f del L by del qk delta qk and plus summation k 1 to f del L by del qk dot delta qk dot. Now let us integrate this delta L between the time limits t1 and t2. So you can say integrating between the time limits t1 and t2. What will be our result? You can see this is integral from t1 to t2 delta L dt. This will be equal to what? As delta L has been defined here, you can see, so this will be simply integral t1 to t2 summation over k. Now I am not writing here the actual limits 1 to f. This k already indicates that k runs from 1 to f, where f is the degree of freedom of our system. So this is summation over k del L by del qk times delta qk, and plus integral from t1 to t2 del L by del qk dot delta qk dot. Say this is equation number 1. Now we know from Hamilton's variational principle that the delta variation of the time integral of Lagrangian is equal to 0. So you can say, but according to Hamilton's variational principle, delta of integral t1 to t2 L dt equal to 0. So as you can see, the LHS of this equation 1 is in fact this delta integral t1 to t2 L of L dt. So by the use of this equation 1, you can write, so from equation 1 we can write that integral from t1 to t2 summation over k del L by del qk delta qk dt. Here actually there will be in fact dt2. When you will integrate with respect to t, there will be dt here. So dt and plus integral from t1 to t2 summation over k del L by del qk dot delta qk dot dt, and this will be equal to 0. So we have written actually the Hamilton's variational principle in the present context. Now you can see from here this delta qk dot may be written as d dt of delta qk, as you have learnt earlier. So this equation may be written as integral from t1 to t2 summation over k del L by del qk delta qk dt plus integral from t1 to t2 del L by del qk dot, and now this delta qk dot, we will write it d dt of delta qk, as you have learnt earlier this fact, and dt this equal to 0. Now this second term in the LHS of this equation will be now integrated by following the rules of integration by parts. Actually here this del L by del qk dot, we will treat it like the first function, and this d dt delta qk we will treat it like the second function. So when you will integrate this by integration by parts, what will be the result? You can now see it. So integrating the second term in LHS by integration by parts. You can see what will be this integral. This term is actually integral from t1 to t2 summation over k del L by del qk dot and d dt delta qk dt. As I have told you that we will treat this del L by del qk dot as first function and d dt delta qk as second function. So now let us apply the formula for integration by parts. You know this is first function. So first function is what? This is del L by del qk dot, and then first function times integral of second function. You can see the integral of d dt delta qk with respect to t will be what? That will be simply delta qk, because you can imagine that this dt will cancel and there will be differential of delta qk, and the integral of differential of delta qk will be simply delta qk. So this is delta qk, and the limits are t1 and t2. Now there is minus sign here, and then integral from t1 to t2. Now we will take the differential of the first function. First function is del L by del qk dot, so its differential will be d dt del L by del qk dot times integral of second function. Integral of this second function, we have seen this is simply delta qk dt. Now see the first term in RHS. As you know, in delta variation, this delta qk vanishes. It is 0 at the end points, and this t1 and t2 actually represent the end points. So at t equal to t1, delta qk will be 0. At t equal to t2, this delta qk will be also 0. So this first term actually vanishes, and its value is actually 0. So you can say, as in this small delta variation, this delta qk will be equal to 0 at t equal to t1 and also at t equal to t2. So therefore you can say this del L by del qk dot delta qk at t1 and t2, this will be equal to 0. And if it is 0, then the second term will be actually equal to minus this much. You can see here. So you can say, therefore, integral from t1 to t2 summation over k del L by del qk dot d dt delta qk dt, this is simply equal to minus integral from t1 to t2 d dt del L by del qk dot delta qk dt. Now we will use this value which we have obtained here in this equation. You can see I have not mentioned the equation number here. Let us say this is equation number 2. So we will use this the result which we have obtained here. At the place of this second term, you will use that result. So you can see, using this result in equation 2, we get what you will get. You can see what is equation number 2. Again, once you see, this is your first term, and at the place of this second term we will write actually this value. So you can write now, this is integral from t1 to t2 summation over k del L by del qk minus d dt del L by del qk dot delta qk dt equal to 0. Say this is equation 3. Now you can see that these qk's are actually independent from one another. When you say qk means q1, q2, so on, qf. And all these coordinates are independent from one another. So these qk are independent from each other, and therefore you can say that this delta qk, this will be also independent from each other. When you say delta Qk, it means delta Q1, delta Q2 and so on delta Qf. It means this equation 3 holds for all values of delta Qk. In fact, this will be possible only when this coefficient for each delta Qk will vanish separately. So you can say then for the validity of equation 3, all coefficient of delta Qk must be 0 separately. It means when we will take k equal to 1, then that coefficient will be 0. If you will take k equal to 2, then again 0. So in general, you can say that del L by del Qk minus d dt del L by del Qk dot, this is Qk dot, equal to 0, or you may write it d dt del L by del Qk dot minus del L by del Qk equal to 0. And you can see this is nothing, this is simply the Lagrange equation for a conservative system. So this is Lagrange equation for a conservative system. So you have seen that using the variational principle of Hamilton, we can easily obtain the Lagrange equation for a conservative system.